Hi, everyone. I am not Hannah Blair.
I know, I was going to say.
I'm Caden Nasworthy. I'm giving the talk on behalf of Hannah, who has to be on a boat today in the Gulf of Maine. But this talk is work that Hannah put together while she was a postdoc at Cornell and is on quantifying fish abundance in the surface acoustic dead zone in Lake Superior and Lake Michigan. It's going to be a lot of more acoustic talks, so hope you are looking forward to more echograms. So acoustic fishery surveys, as we've talked about for the past few talks, are commonly used in the Great Lakes to estimate fish abundance. And we get estimates of, don't know how that works. There we go. Of echo intensity, backscatter. That is the echo of the sound we transmit into the water column back to the transducer located at the vessel at the surface. You get measurements of the total amount of energy coming back, as well as the target strength from individual fish in the water column. And an example of this echogram here, you see the vessel moving from left to right across your screen, traveling, covering a certain amount of distance. The y-axis is the depth of the lake with the surface on top and about 80 meters depth of the lake bottom. This dark red is the acoustic return from the lake bottom. And you can see scattered fish targets deeper in the water column as well as up towards the surface. So to define the surface acoustic dead zone, the downward-looking transducer is located some distance below the surface of the water, and that is due to the depth of the hull of the vessel. And then there's also the near field of the transducer, where the actual transmitted pulse is not yet in a consistent arrangement, I guess, to get consistent results back. So you have a combined area of about 4 to 5 meters, depending on how deep that transducer is in the water column, where you cannot get accurate estimates of fish abundance. To enter the long-range autonomous underwater vehicle, LRAUV, the specific name for this one is the Triton, or the Tethys class, and the specific vehicle is the Triton. These are autonomous vehicles manufactured out in California by Monterey Bay Aquatic Research Institute. They are battery powered and buoyancy powered, and they collect acoustic data with 4 different transducers, 2 looking up and 2 looking down. So you can collect a lot of different data. You get 2 different kinds of frequencies, in this case, 200 kilohertz and 333 kilohertz. These are underwater drones, so rather than being at the surface of the water, you give it a certain depth to dive down to, and then it does the survey. The max speed of these drones is approximately 1 meters per second. And then as these drones go through the water column and they go back up to the surface to receive information from the satellites and transmit its location back, it collects environmental data profiles as it goes through the water column. So here's an example of an echogram from the AUV. Rather than having a black box at the surface where the vessel would normally be, we see the drone traveling at approximately 25 to 30 meters depth as it goes through the survey. We see the red strong echo of the lake bottom, as well as a red strong echo on top, and that is the surface of the water column. That's the sound reflecting back from the water-air interface. And so this allows us to look at fish densities that we normally couldn't see in this 5-meter zone from the surface to 5-meter depth. So the main research questions are: how much fish are in the surface acoustic dead zone in the top 5 meters? Can we correct for that bias? And what variables are associated with higher proportions of fish in the dead zone? Going to the first question, how much fish are there in the dead zone? And then what proportion of aerial density does this represent? Looking at data collected in the summer of 2022 in the western arm of Lake Superior, as well as the southern basin of Lake Michigan, these drones traveled on this white sampling path, and then the dark paths here are the nighttime sampling effort, and these yellow circles are those profiles the drone takes as it goes up and down in the water column. So we used single echo detections, SED, so picking out individual fish in the water column. We used the distribution of those single echoes over a 2-kilometer transect horizontally. The vertical depth of those bins varied from, they're all 5 meters, 0 to 5 meters on top, 5 to 10, and then going down. We used 2 different single target thresholds to determine what we're classifying as a young of year fish, for example. In Lake Superior, the young of year class size is anything smaller than minus 50 dB. And in Lake Michigan, it was minus 55 dB. The fish communities of these two lakes are different. In Lake Superior, we have shallower Cisco shallower fish such as Cisco, as well as rainbow smelt, and then young of year assemblage of Ciscos, including bloater and kai as well. Deeper in the water column, you see more bloater and kai. In Lake Michigan, you see more alewife, rainbow smelt, and bloater dominated community. In Lake Superior, Cisco like cold oxygenated waters, less than 20 degrees Celsius. This paper from Dan Yule shows the expected distribution of different species across different depths and bathymetric depths in Lake Superior. So looking at the fish densities in each 5 meter depth layer in Lake Superior, we did see the highest densities of fish in the top 5 meters in the 5 to 10 meter layers. And that's exactly where we'd expect to see the young of year fish. Looking at it proportionally of overall fish targets in the water column, in Lake Superior, we found there was a median of 32% of total fish targets in that upper 5 meters of the water column. When we break that out into different size classes, looking at young of year fish and then yearling and older fish, a dramatic difference where we really are seeing over half of the young of year fish in that year in Lake Superior were in the top 5 meters, whereas it was not as big of an impact for yearling and older fish. Looking at the fish community by depth in Lake Superior, this year we did have a large year class of Cisco in 2022. These distributions show that shift of smaller targets towards the surface, and then as you get deeper into the water column, you get larger targets dominated more by kai and bloater. This is an example echogram showing that we can see fish in this upper 5 meters. Normally, the vessel would come down to this depth here, and the near field would come down to 5 meters, so you wouldn't even be able to see this whole area. And then this is just showing examples of how much Cisco they had in Lake Superior in 2022, especially this bottom right bar. In July 2022, they caught a record amount of young of year Ciscos. Moving over to Lake Michigan. Lake Michigan had higher densities lower in the water column compared to Lake Superior, more so in the 20 to 40 to even 60 meter depth range. Looking at it proportionally, in Lake Michigan, it was a much smaller proportion in the upper blind zone of 3% of total fish targets. Breaking it down into size class did not have a huge impact, and it's only 5% of young of year or 2% of yearling and older fish in the upper blind zone. The Lake Michigan shallow prey fish community is dominated by alewife, which like warmer waters, and they do stratify based on their life histories as well. And these are some examples of the profiles collected from the AUV as it transits through the lake. Each one of these facets is a single transect, and then each profile is one of those yellow dots along the survey track. I was personally kind of surprised at how variable that these thermoclines were in different locations of the same transect. Rainbow smelt also are present in Lake Michigan, but they occupy typically more nearshore habitat compared to alewife. And this is a similar expected distribution of fish species in Lake Superior as to what we'd expect in Lake Michigan as to what we saw in Lake Superior. So to sort of look into the upper water column a little bit more specifically, since we saw very little effect on the overall fish community in Lake Superior, looking at just epilimnetic and metalimnetic fish targets, there is a median of 13% of targets in that upper 5 meter water column. And then broken down into size class, it was 15% of young of year and 11% of yearling and older. So it looks like in surface oriented fish in Lake Michigan, less of an impact in Lake Superior, but still about a 15% bias. So can we correct for this bias? We're going to quickly test for a simple correction factor that can we assume that the densities of fish in the 5 to 10 meter layer are exactly the same as 0 to 5 meter layer? We used a one sample Wilcoxon test of differences of paired transects or sections of transect in the 0 to 5 and 5 to 10 meter layer of water. That red line is the median, right there. In Lake Superior, on this upper plot, it looks like no, you can't use the same densities of fish in the 5 to 10 layer as the 0 to 5 layer. There was a higher density of fish in that top 5 meters of the water column, and that was a relatively large effect size. However, in Lake Michigan in 2022, we can use a simple correction factor, and the densities in 0 to 5 and 5 to 10 were very similar. And then briefly going to go into some preliminary modeling work that they've been working on different variables that are associated with proportions of fish in the dead zone. Eventually, we want to look at what environmental drivers could be useful in predicting the distribution of fish in the water column. In Lake Superior, through their model analysis, they found a significant impact of bottom depth, surface temperature, metalimnetic depth, as well as the chlorophyll density in the top 5 meters of the water column, with very negative and positive relationships seen here on these partial effect plots. In Lake Michigan, they also found similarly effect of bottom depth and top 5 meter chlorophyll A density. However, they also found a significant effect of air intrusion depth, and then thermocline depth had a weaker but still significant effect. So some key takeaways to this work: long-range autonomous underwater vehicles can measure fish abundance in that top 5 meter water column, the surface acoustic dead zone, that surface-based platforms would miss. This could potentially be a large proportion of fish, from 15 to 30% or more, that are in that top water column. There are strong implications that young of year fish occupy the near surface, and so specifically maybe missing the small young of year fish in your estimates there. And then a highlight that fish community and year class really does matter. These are just a couple examples from 1 year in 2 different lakes. So there could be different results in a different year class of Cisco, for example. Simple correction methods can work in some communities, but not all. This also could work in some years, but not in others. And then there are beginning to work on predictive model-based correction methods using different environmental covariates to potentially model this in the future. And that is all I have. I will attempt to answer any questions, and thank you.